Everyone, in this video I'm going to show you a code for the Navier-Stokes equation. Let's just run it and see what it does. So this is a driven lead cavity problem, and as you can see the code works pretty decently. This code I wrote based in 2 papers that I'm going to post in the description of the video along with the code itself. So now the simulation is finished. Let's just take a look into the code and change some parameters to get a different solution. So let's just start at the beginning. Here we have a number of points. You can choose a different number of points in the x and y direction, and you can change the domain size. Let's say you want a more horizontal domain, so just let's put a length of 2 and a height of 1, and let's just give it more points in the horizontal direction since we just double the dimensions. This is the dt, the delta t. You have to be careful with that because if you change, for example, the mu, which is the viscosity, let's just put a lower viscosity, which means a higher Reynolds number, you should decrease your dt because of stability constraints. Okay, this is the number of steps that the code is going to run. And here are the boundary conditions for the tangential velocity. You can choose, for example, horizontal velocity. Here we have a north face of 1 and the rest is 0. We can just say a vertical velocity in the west face. Let's put it 0 negative. We can also put negative 0.5. Let's see what it's gonna give us. This is the maximum iterations for the Poisson equation for the pressure, and this is just a parameter that's gonna how many iterations we plot. Okay, and here's if we want to plot the vorticity. Okay, so now we're just going to the code. We're initializing our variables. We're working with a staggered grid, so here you can see the dimensions of the matrices U, V, and P. Here are the temporary pressure, velocity, and auxiliary variables. Okay, so here we're just following the steps on the papers for the boundary conditions, and here for the temporary velocity and temporary U and V velocity. I didn't mention, but I'm using the MAC method, marker and cell method. So now that we have the temporary velocities, we solve for the pressure. We have Newman boundary conditions for the pressure, and we solve by iterations. This code is fully explicit. I don't have any implicit solving of equations, which is nice because you can adapt the code to more complex domains easier, but it gives us strong constraint on the time step. And once we have the solution for the pressure, I give it an error of 10 to the minus 5, which you can change. I think it gives us good results. We correct the velocity, and if it's the correct iteration, we plot the results. So it's very easy to understand. I try to write it fully vectorized to optimize the time. But now let's just see the solution with these new parameters. Let's see what it gives us. you can all see that the code is working fine. I hope you can take a deeper look into what it does, and then you can just develop new codes based on this, or you can understand the method based on this code. I'm also gonna post more videos in which I modify this code to put inflow boundary conditions, to do obstacles, flow around a cube, and various problems, and coupled with the heat transfer. So this is the first of a series of videos. Thank you for watching. I hope you enjoyed it.